Hello everyone, welcome to the Department of Chemistry, IIT Delhi, and hope all of you are doing well and staying safe. And thank you very much for joining this webinar today. My name is Soumik Siddhanta and I'm the webinar facilitator and an assistant professor at the Department of Chemistry, IIT Delhi. And we are very pleased to bring you this content today, which is the part of the online Pratidhwani series that the department is organizing. The webinar series is sponsored by Author Cafe. Author Cafe is an online platform that aids in writing, collecting, organizing, collaborating, and publishing your research content through features and integrations which products like Mendeley, Zotero, Orchid, Crossref, and so on offers. You can think of it like Google Docs, specially designed and developed for the academic community and much more. So today we are thrilled to have Professor K.L. Sebastian from the Indian Institute of Science, Bangalore. And before we start, a couple of technical details. Please do not unmute yourself during the talk. If you have any questions, please type them in the chat box and we will try to get some of them through to the speaker after the talk. And now I would like to request Professor Sajesh Thomas from the Department of Chemistry, IIT Delhi, to introduce the speaker today. Over to you, Sajesh.
Thank you, Dr. Soumik Siddhanta. And it's a real pleasure to introduce Professor K.L. Sebastian. For those of you who don't know, the students, some of the students, I should introduce Professor Sebastian. He was a professor and dean at IIT Palakkad, and prior to that, he served as a professor for a long time and as a head of the department in the IPC department, Indian Institute of Science, Bangalore. His research interests include quantum chemical calculations, chemical reaction dynamics, chemical applications of density function theory, theory of electron transfer reactions, and statistical mechanics and dynamics of polymers. And it goes on. He has worked on a number of areas where he has applied these theoretical techniques. And he was awarded the prestigious Bhatnagar Prize in Chemical Science in 1995 when he was working in Cochin University, I guess, and soon he moved to IISc Bangalore. And he was also awarded J.C. Bose National Fellowship in 2008. And most recently, he was awarded the prestigious CRSI Gold Medal of 2021. I mean, it was announced last year, but it was the gold medal for 2021. CRSI, the Chemical Research Society of India. And for those of you who don't know, it is the Lifetime Achievement Award given to a person of high eminence with a lifetime contribution to chemistry. And also, he was awarded Swadeshi Shastra Puraskar from the Swadeshi Science Movement in Kerala. And if I keep on going on the number of awards and recognitions awarded to Professor Sebastian, it will take another half an hour. So, he has served as an associate editor and editorial board member of several journals, including Resonance, Computational and Theoretical Nanoscience, Pramana, etc. And I think he has published more than 130, 150 peer-reviewed research papers. So, yeah, forgive me if I'm not updated on your number of papers, but this is what I got. And above all this, Professor Sebastian is one of the most renowned quantum chemists of the country, and he's very famous for his excellent teaching. And personally, I've been fortunate to attend his quantum chemistry classes when I was a student in IISc Bangalore, and his lectures are extremely popular in YouTube, the NPTEL lectures on quantum chemistry. So, yeah, I may not be too qualified to explain to you what are his major contribution, the scientific contribution to the field. But from what I gather from the internet, some of them include his development of time-dependent version of coupled cluster theory, and more importantly, the kink mechanism for the translocation of long chain molecules. Yeah, with that, I will welcome Professor Sebastian. A very warm welcome And over to you, Professor Sebastian.
Thank you, Professor Jesh. It is indeed a pleasure for me to be giving this talk. I would like to thank the Department of Chemistry of IIT Delhi for giving me this opportunity to talk about my work. I mean, Sajesh qualified me as a quantum chemist, but unfortunately, I'm not speaking on quantum chemistry, quantum chemical aspects. What has happened is that, you see, I have been doing different things. So the talk that I am going to give today is based upon the PhD work of one of my students, which has been, this most of it, I mean, after my retirement from IAC, so it was done essentially in IIT Palakkad. I would, of course, like to thank IAC, which has always supported me. It supports me all the time, even now. And IIT Palakkad for being the host when this work, I mean, at least a major part of this work was done. So with that, I would like to start my presentation. First of all, I would like to wish you all a very good afternoon and pass on to the title of the talk. This talk is actually about diffusion in a crowded and changing environment. Of course, it is given at the Department of Chemistry at IIT Palakkad, sorry, IIT Delhi. And here is my name and my address, my affiliation essentially. But of course, you see, I'm not a faculty member anymore. I'm a retired faculty member. And this talk is about some aspects of diffusion. And when you hear that, you say people will definitely say diffusion is a very old subject. Is there anything new? And in fact, there are many things that are new, and that is, I'm going to talk about one of the things that are new. So here is an outline of my talk. I shall remind you what is normal, what is meant by normal or Brownian diffusion, major aspects of it. This is actually very well known and everybody knows this. Then I shall give you some experiments where diffusion in crowded or rearranging media have been studied. And in some sense, the diffusion in such media has been found to be Brownian, but at the same time anomalous. It is different from Brownian. It resembles Brownian motion, but not exactly. And there has been a model that was suggested by Chubinski and Slater, and they did computer simulations of this model and arrived at results that are in agreement with the experiment. And our own interest has been to construct an analytical model for the same. Even though I say analytical model, I will try to restrict the mathematics to the minimum possible so that it is clear to the students. I hope it will be clear. And then after describing our model, I shall talk about what are known as first passage problems. First passage problems are very well known. But here is the twist, it is in a crowded medium. Then I shall talk a little bit about rotational diffusion in crowded media. I'm not going to go into the details of the derivations, which I'm sure most of you will find boring. So I shall tell you what has been done. Then I shall also talk about diffusivity that is changing. The diffusivity itself undergoes anomalous diffusion. I shall explain what is meant by this. Then give a summary of what we have done and end with the acknowledgements. So this slide is regarding normal Brownian motion. So you have to imagine that this is a large tube filled with water, and imagine that you have put a a substance that is a dye, colored blue color, has been put here initially, and it forms a narrow band. And imagine you plot the concentration along this line. Right? How does the concentration vary along this line? As a function of position. Position will be denoted by x, and if you plot that, you see you are going to get such a curve. Okay? So this is at the initial time, and then suppose you wait, what will happen is that the concentration profile will spread. That means this band will become wider and wider as time passes. So this is what will happen. The concentration will spread. And therefore, if you are plotting the concentration profile along this line, what will happen? That also will spread. So therefore, the concentration profile C of xt is a function of position and it is changing as a function of time. So that also will change, and this is what will happen. So this is all very clear and simple. And now if we look at a particular molecule of the dye which is in the solution, let us say it is starting here. What does that molecule do? Well, it executes random motion or Brownian motion, like the one that is shown here. The motion is erratic. The dye molecule wanders in different directions. And therefore, if I'm thinking of a single dye molecule, I cannot talk of concentration, but I have to talk of the probability density, P of xt, the probability density of finding the particle at x at the time t. So this is the quantity that one would talk about if I am concerned with a single molecule. And the theory of this is actually very, very well understood. The equations are well known since the 19th century. And if you think of the concentration profile, or if you think of the P of xt, if you are concerned with a single molecule, you would talk about P of xt, while if you are concerned with a macroscopic number of molecules, then you would talk about concentration. But most of the time I shall be talking about single molecule or a single particle, and therefore I shall talk about P of xt. So P of xt has this shape. At any given time, it has this shape. And if you ask mathematically what is this function, then P of xt is given by this expression. Now in here, what the important thing to notice is that this is a Gaussian. It is a Gaussian. You have e to the power of minus x square in the expression. So x square is in the exponent. So therefore, this is a Gaussian, which means that it has this shape. And you also should notice that there is time here in the exponent, but in the exponent it is occurring in the denominator. And this simply means that the width of this Gaussian is changing as a function of time. And so therefore, if you look at the width, well, it is a Gaussian, and that is what we refer to as the width. And the width, because there is a time in here, this width is changing as a function of time. And as time passes, the width goes on increasing. So how does it increase? Well, in fact, the width goes like square root of the time. So therefore, suppose you are able to experimentally observe this profile, then you can say the following. Imagine you take the square of the width, it will be proportional to time. And so if you plotted logarithm of width square against logarithm of time, you will have a slope unity. And this is a usual procedure that experimentalists do to determine whether the diffusion is normal and Brownian. So what is the idea? You observe the profile, concentration profile, determine the width, plot logarithm of width square against logarithm of time, and if it has a slope unity, then you immediately say, okay, the diffusion is normal and it is Brownian diffusion. And I should tell you also that this constant here, d, written there, is known as the diffusion coefficient of the particle, and for a particle it is a constant. Imagine you have a particle in a homogeneous medium, then the diffusion constant is always a constant. So now let us look at some experiments that have been done roughly 6 or 7 years ago. And these experiments have been done in the case of diffusion in a crowded and rearranging medium. And how was the experiment done? Well, the experiment was done with colloidal particles, and they used a single particle tracking. So you can track the movement of a single particle and measure its displacement as a function of time. So, but before I go into that, you may ask, what is the crowding due to? Well, if the crowding itself may be due to other colloidal particles, or maybe due to macromolecules, filaments, or maybe the diffusion is happening in a glassy material. So there are different cases that you can think of. But the experiment that we are concerned with were done with the diffusion in one dimension actually. Why one dimension? Because the colloidal particles were stuck to a tube, a lipid tube, which has a diameter of 100 nanometers. And it was observed that these colloidal particles are free to move along the tube, but they could not detach themselves from the tube. So therefore, at all times during the movement, the colloidal particles were attached to the tube. And the tube has a diameter of 100 nanometers. The colloidal particle also has roughly the same kind of diameter. And they studied two different cases. And in both the cases, they plotted the logarithm of bit square against logarithm of time. And this is actually the experimental result for the first case. This is the result for the second case. That is the result, which means that in both the cases, the diffusion appears to be completely normal, obeying whatever laws of diffusion. So let us look at the two cases. This is actually DLPC lipid tube. So you put the colloidal particle on DLPC lipid tube. The expansion of DLPC is shown down here. And when they look at the diffusion coefficient, they find that the diffusion coefficient is 0.4 micrometer square per second. Okay. And then what they did was, you see, they said, okay, the tube is actually quite flexible, so let us make it rigid by incorporating cholesterol in it. So they incorporated 40% cholesterol in the tube, as a result of which the tube became very rigid. And on the rigid tube also, you see, they found that the diffusion is Brownian. That's what they thought. But the diffusion coefficient is much reduced. It is only 0.012 in comparison with 0.4 that was observed in the earlier case. Why is it that the diffusion coefficient is larger in this case? Well, the answer is simple. The tube is flexible, so while the particle is moving, you see, the tube is fluctuating, and that adds to the diffusion. So the fact that it is flexible is actually contributing to the diffusion, and that is why the diffusion coefficient is larger. But in both the cases, it seems to be normal diffusion. But then what they did was, the experiment was done by Granick et al. They measured the probability distribution so that they can see these Gaussians. So when they did that, they found that it is Gaussian. Only in one case, in the other case, it was not Gaussian. In fact, in the case where the tubes were made stiff by adding cholesterol, they found that the probability distribution is Gaussian, but not in the other case. In the case where the tubes were flexible, they found that the probability distribution is not Gaussian. So let us see what the experimental results are. So here again, remember, we are going to plot logarithm of P of xt against x, against position. Remember, P of xt is given by a Gaussian, so therefore this is having an exponential form, and if you took the logarithm of that, what will happen is that you will get an x square, which essentially means that your result should be a parabola. So it should have a shape which will be something like this. Right? An inverted parabola, because it is exponential of minus x square. But when they made the experiment, actually at short times, short meaning 0.06 milliseconds, they did not find a Gaussian profile, but instead they found that the plot is looking like this, which means that the profile is exponential instead of being Gaussian. Then as time passes, what happens? It is still exponential, at least in these regions. Here there is some portion that tends towards a Gaussian, but essentially here it is linear. So it is still exponential. Even here it is exponential. But in the very long time limit, very long time meaning in this case 60 milliseconds, the profile is actually a parabola, inverted parabola, upside down parabola, and therefore at this point the profile is Gaussian. So therefore, what is the experimental observation? Well, these are the experimental observations with the actual experimental points. So initially the profile is exponential, but then as time passes, you see it smoothens, and at later times it becomes Gaussian. That is the experimental result. So this was around 2012 or so, but roughly the same, well, a little bit earlier, there were experiments carried out on worms. Of course, you see, nobody in chemistry knew of these experiments. Only I became aware of these experiments only something like 2 years ago. Even though they were reported in 2009, the experiment was done with very small, very tiny worms. These are worms that infect snails. So they observed the random walking of these worms. Okay. So this is the worm, that is the biological name for the worm, which I am not going to read out. But remember, these are very small, 1.3 to 1.7 millimeters in size. And they will execute walks, and you can observe them collectively. And I want to show you the experimental results, which were reported in the paper that I showed you. So when you look at them collectively, what you find is that the probability distribution is always exponential. Always, at all times, it is found to be exponential. This means you are looking at the random motion of a large number of worms collectively. On the other hand, if you look at the motion of, study the motion of a single worm, right, in the random walk, then you find that it is always Gaussian. So this seemed to be strange. On a collective level, it seemed to be exponential, but at a single, I'm tempted to say molecule, single molecule, but of course I should say single worm level, it is actually a Gaussian. So what is happening? Gaussian at individual level, but exponential at the collective level. The explanation that the biologist gave is very simple. You see, the worms are not all the same, while molecules are all identical. So different worms have different walking abilities, and therefore they will diffuse at different rates. And therefore the diffusion of the first worm, so each worm has its own diffusion coefficient. So therefore, if you are thinking of the first worm, you see the probability distribution function for it would look something like this, the black curve. For the second worm, the diffusion coefficient would be perhaps larger, and therefore you would have that curve. For the third, it is even different. For the fourth, it is still different, and so on. So therefore, if you wanted to get the collective probability distribution, what you should do is you should sum up all these. You have to sum up all these Gaussians, and interestingly, these Gaussians are added up in such a fashion that the result is exponential. So this is essentially a weighted sum of Gaussians, and that is actually an exponential. And so that was the explanation that was given by the biologist. But in this case, the exponential never changes over to Gaussian, while in the case of molecules, what happens is that it is exponential initially, and later times it changes over to Gaussians. But of course, I have indicated the major difference between colloidal particles and worms. Each worm has its own diffusion coefficient, but you see colloidal particles are all identical, so their behavior you would expect is identical, not different. So therefore, you see colloidal particles are not worms, but for short times the probability distribution is exponential, so it would be given by some such expression for short times. And further, you see there is a lambda, a factor here. It is proportional to square root of t. Essentially, what I am saying is that the width is proportional to square root of the time, just as in Brownian motion. But at long times, it becomes Gaussian. But interestingly, in the case of colloidal particles, what you find is that at all times, width square is proportional to time. That was seen from the experiments, which means that if you calculated the width by taking the expectation value of x square, then you find that it is always proportional to time, whether it is exponential or Gaussian. Even initially, it is proportional to time, and even at long times it is proportional to time. So that these are the experimental observations. So therefore, what is the explanation for this? An explanation was offered by the original author, which is Granick, who is Granick, and then these authors who published a paper in Physical Review Letters in 2014. And their explanation is this. You see, imagine you have a particle, a colloidal particle, which is diffusing. And let us say that it is diffusing in a crowded medium, something like this. The diffusion coefficient of this particle, because of the crowding, will be different in different locations. So this is a picture where the diffusion coefficients are color-coded. For example, you see if it is a dark, the diffusion coefficient is very large, 0.6. So here the diffusion coefficient is quite large. While in blue regions, for example, somewhere here, the diffusion coefficient is very small. So here you see, I am assuming that the medium is static. And imagine that the particle actually starts diffusing, as you can see here. So in such a case, what happens, you see, when the particle is diffusing, it is visiting different regions in the medium. And in different regions, the diffusion coefficient is different. So even though the medium is static, because of the fact that the particle is moving, the diffusion coefficient actually changes as a function of time. So even though the medium is static, because the particle is diffusing, there is a change in the diffusion coefficient, and the movement of the particle is random. So therefore, essentially what will happen is that the diffusion coefficient will change in a random fashion. It is also possible that the medium is not static, which means that the crowders will rearrange, and that will also change the diffusion coefficient in a time-dependent fashion. So therefore, the central idea is that the diffusion coefficient is changing as a function of time. It maybe the particle has moved to a region where diffusion coefficient is different, or maybe because the medium itself rearranges. These two possibilities definitely are there. So therefore, what we are saying is that, you see, when we are observing the diffusion coefficient is actually kind of changing as a function of time. So how would you change where it is changing in a random fashion? So therefore, if you are able to study the diffusion coefficient, what happens is that the diffusion coefficient is fluctuating in this fashion. Okay. So if you plotted d as a function of s is my symbol for the time that is passing. T will be used to denote the final time. That is why I'm using s to denote the time. And the diffusion coefficient is going up and down as a function of time. But then, of course, you see, even though we are saying that it is changing as a function of time, always diffusion coefficient by definition is a quantity that is positive. So d of s is always positive. It has to be greater than or at the most equal to 0. So therefore, the question now is, what is the probability distribution in such a case where the diffusion coefficient is changing as a function of time? Well, before that, we have already seen that if the diffusion coefficient is a constant, the probability distribution is given by this expression. So strictly speaking, what I should do is, if d of s is time dependent, then what I should do is I should solve the so-called diffusion equation with the time dependent diffusion coefficient. It is not difficult. I have not written the equation, but if you solve it, this is the expression that you will get. But even though we have not solved the diffusion equation, we can easily see what is happening. You see here you had d into t. If you have a constant diffusion coefficient, all that you need to do is you have to multiply d with the time. But if you have a time-dependent diffusion coefficient, all that you have to do is instead of that d into t, you have to have the integral of d of s from the initial time 0 to the final time t. And you have to put that in here instead of dt, and there also instead of dt, you have to put that, and this is the expression for the probability distribution. But then you see, remember, d of s is random. So if I do one experiment, you see, you will get p of xt, but in that particular realization, d of s would have behaved in one fashion, while in the second case, it would have be in a different possible realization of the d of s. Diffusion coefficient would vary in a different fashion in the second possible case. So therefore, what I should do is I should repeat the experiment and take the average over all possible ways in which the diffusion coefficient can change. And therefore, you have to average this over all possible realizations of the diffusion coefficient, which is what is done in the next slide. So this is b of xt for a particular realization of the diffusion coefficient. But then if you do the experiment averaging over all possible realizations, theoretically also you will have to realize over all possible realizations of the diffusion coefficient, and that averaging I indicate by this kind of two brackets indicate that you have to average over possible realizations of d of s. But then is it possible to get some analytical results where it is possible to get analytical results if t is very small? Because if t is very small, you can say during that very small time interval, the diffusion coefficient can be considered to be a constant. So d of s is a constant, but then in different experiments, you see this constant is going to be different. So therefore, the probability, the d of s now becomes a random variable p of given by a probability distribution p of d, which if you assume is exponential, then the averaging can be done easily. And if you did the averaging over such short time average, essentially what you will get is this exponential distribution, whose width is proportional to square root of t. So therefore, at least for short times, you can do an analytical derivation and show that the probability distribution is exponential, and the width of this exponential is actually proportional to square root of time. So that seemed straightforward. But what about longer times? You see, at longer times, we know that the probability distribution switches over to, it becomes Gaussian. And so can we do an analysis for longer times and show that it becomes a Gaussian? Well, Chubinski and Slater did simulations, and these are the simulations that they carried out. At short times, they found that it is exponential. That is what is shown here. Right? It is a logarithmic plot of probability against position, and you get a straight line, which means it is exponential. But at longer times, you are getting a parabola, which means that it is changing over to a Gaussian distribution. So these are actually the results of Chubinski. And our own question was that, you see, whether we can develop an analytical approach which is valid for all times, valid for short times as well as long times. So what is the problem? Why did Chubinski and Slater have to do computer experiments? That is because, you see, you take this quantity and you have to average it over all possible realizations of this. And if you look at this expression, you see the quantity that is to be averaged is actually over the random function d of s. And that is occurring in the denominator in two places. It is occurring in the exponent in the denominator, and it is also occurring here. And therefore, you see, nobody in the right senses would say that you can perform such an average analytically. So for this average seemed to be extremely difficult, and that is why the computer experiments were done. Well, but interestingly, there is a trick. At least for some models, this can be done analytically, and that is what we did. So what is the trick? The trick is actually, if we look at this expression, it seems very complicated and very difficult to perform averages over. But if you look at it, stare at it hard enough, then you will realize that you see this can be written as a simple Fourier transform. See, you are performing a Fourier transform. That is what this exponential of IPX, which is occurring there, is meaning, and you are integrating over all possible values of P. So as you are performing a Fourier transform, what is the quantity that you are Fourier transforming? It is a simple exponential. Exponential of minus P square integral 0 to T d of S P of S. So essentially you have the integral of the diffusion coefficient in the exponent. You don't have this integral in the numerator or anywhere, but it is simply in the exponent. And a quantity which is in the exponent can be easily averaged. In fact, when I give you this equation, you would think that this was very easily to obtain. But actually what we did was we used a very complicated path integral approach to arrive at this expression and published a paper using the path integral approach. And after publishing this rather complicated paper, we realized that there is an easier shortcut. This always happens. Well, if you know the result, then you say there are any number of simple ways of deriving that simple result. It may turn out. So therefore, I am telling you the simple approach that we realized only after doing the complicated derivation. So therefore, this quantity can be written as a simple Fourier transform. And then you can perform the average. You see, now you have to average this exponential quantity. And averaging something that is exponential is fairly easy. I mean, not very easy, but it is fairly easy. So how do you perform this average is the next question. Well, the answer is that you see we constructed a simple model for DFS so that we can perform this average exactly on paper, not on a computer. So what is the problem? You have to calculate this, and let me look at the previous expression once more. Yeah, you have to calculate this average, and then you have to take the Fourier transform. So therefore, if you define a new quantity, which is the expectation value or the average of this, which is what is done in this slide, that you have to calculate this average. And once you calculate this average, you simply have to take the Fourier transform of that, and you will get the probability density function that we are trying to calculate. So the problem, as I told you, is we have to construct a model for the diffusion coefficient. So how do you model the diffusion coefficient itself? And you have a very big constraint. The constraint is that you see you cannot allow DFS to go below 0. It has to be positive. So what was the model? Well, we hit upon a simple model for the diffusion coefficient for which we can actually do the calculations completely analytically. So what is our model? Well, we think of, well, we have the colloidal particle that is executing the random walk. That is what we do the experiment with. But we now want to model DFS, and the model that I'm introducing actually involves random walks. So therefore, you think of a random walker. So here is my random walker. He is a drunk and he is executing a random walk, and he is walking on a plane, let us say. So this is his starting point. At any time, yes, his displacement vector is denoted by this. And because he is walking about randomly, what will happen is that this CFS will change randomly. Right? He can even go off to infinity, and therefore this CFS can go to infinity given enough time. But this is a vector, but you see, we want to have a model for DFS. So what would be the model? Well, what we said was that, okay, let us take DFS to be the square of its distance from the origin. So if you take this vector quantity and took its square, it is guaranteed to be positive. And of course, usually it will be greater than 0. So therefore, our model for diffusion coefficient is to imagine that we have a random walker. This you can, I'm only giving you a specific example, but there are other models that we can easily construct for which things can be done. So for this simple model, d of s is taken to be the square of the distance of the random walker from the origin. This ensures that d of s is positive, but there is a problem with this model. What is the model? Well, the distance can be infinitely large. So the random walker can go up to infinity, while diffusion coefficient is constrained to be less than infinity. It has to be finite. So therefore, it was necessary to modify this model. And what we did was to say that, okay, here is the random walker, but he is not walking in free space. He is confined to the vicinity of the origin. He is walking in 2 dimensions, and we put a parabolic potential. A parabolic potential will constrain the random walker to a finite region of space around the origin. So if he is walking, you say he is constrained by this parabolic potential, and therefore he is constrained. He will not go to infinity, but his walk will remain finite, as of which the diffusion coefficient, which is actually taken to be the square of his displacement, random. That is his distance, and his calculate expected value of the. So if you think in the what you have to, this random walker, when he's walking, probability of killed, I don't say killed, probability of being absent, and that probability of being absent be and import the square of his distance from the origin. That is what this essentially says. So therefore, let me summarize the model. The model is actually you have a random walker who is confined to a region of space by a potential which is harmonic. But further, if he is walking funded far away from the origin, a very large chance being removed. So this picture is a coded representation of his absorption probability. You see the there's a large probability that he will be removed. And so essentially you want to calculate the survival probability of such a walker, while if he is in this vicinity, you see he is not removed, because there the probability of him being absorbed is very small. Why we have all these complications? Well, you see this actually simplifies the problem, because you can do calculations now analytically, because everything is harmonic. So this is essentially a model in which you have a random walk with absorption. And in fact, the probability distribution of the colloidal particle is shown to be equivalent to the survival probability of a random walker who is being absorbed. And that analytical calculation is not very difficult. We did the calculation. This is the mathematical expression that you would get. And once you took this and took its Fourier transform with respect to P, you will get the probability distribution, P of xt. Now, once you get such a result, it is very easy. You can easily analyze it, right? This alpha, which is occurring here, is given by this expression. You can easily analyze it in the short time limit. Once you have a mathematical expression, it is easy. And show that it is exponential. Then at long times, you can also show that the survival probability reduces to being a Gaussian. Being a Gaussian, essentially, the probability distribution becomes Gaussian at long time scale. So therefore, and further, you can also show analytically that the width of the distribution at all times is proportional to time. So that was our analytical result. Remember, these were the experimental results. The computer simulation results of Jubilee et al., which agreed perfectly with the experiment. So therefore, we made a comparison of our analytical results. Our analytical results are the full lines, and these points are the simulation results of Jubilee et al., and you can see that the agreement is perfect. So therefore, you see, we have an analytically solvable model which fits the experimental data perfectly. Well, after we published this, you see there were other models along the same lines suggested by these people. Professor Charail in my own department constructed a somewhat slightly different modified model essentially. Then with that, you see, we got interested because we solved this, we solved the problem exactly analytically, and there was perfect agreement. We then asked about first passage time. So what is first passage time for the students? I imagine that I have a random walker on a hill which has this kind of shape. It is flat at the top, and then you can if you are executing a random walk, definitely you can reach the boundaries of the region. And once you reach the boundary, if you are drunk, it is quite plausible that you would fall off to the ground. And if you fall, you see, you will die. So let us think of such a random walker. So eventually it is clear that he will reach a boundary and then fall off. And then you ask the question, how much time would he walk before he falls? Right? So that actually, or what, right? That is the quantity which is known as the first passage time. This is of great importance in so many problems, particularly imagine you have a molecule which is inside a circular region. If you like, you can imagine that this is a cell, this is the cell wall, and you have a molecule, and this molecule has to diffuse, which essentially means that the molecule is diffusing. And the question is, when does it reach the cell boundary for the first time? That is what is known as the first passage time. Okay, so therefore he will, the molecule will diffuse and reach the boundary. So this is known as the first passage problem. This is very well studied. In fact, you can also ask at any given time, what is the probability that such a walker will survive? And that is known as the survival probability. So in fact, there is a very nice book, A Guide to First Passage Processes, published by Sidney Redner, where such problems have been studied. But then you think of diffusion inside a cell. Okay. But inside a cell, you see, it is not homogeneous medium. The medium is crowded. And the diffusing particle is diffusing in a crowded environment. It has to avoid the crowdeds and eventually reach the boundaries. So this is the problem that occurs in biology, while the problem for which we have the solution is the previous one, where the diffusion is happening in a homogeneous medium. So therefore, you see, we realize that there are no results for this first passage problem in a crowded medium. And so we try to analyze this first passage problem in a crowded medium. In fact, there have been experiments done in biology as to the effect of crowding on the diffusion coefficient of different particles. You see, for example, this is a particular rather big molecule which is diffusing in presence of a crowder, and you can see that different concentrations of the crowder actually changes the diffusion coefficient. So essentially our problem, if I may show it in a cartoon fashion, this is the problem. The medium is changing perhaps, and anyway there is crowding, and what is the first passage time? This is a problem that we could find solutions analytically. We will not go into the details of this analysis, but let me tell you the results on the survival probabilities. Here the variable that is being used is tau. Tau is a scaled time multiplied by the average diffusion coefficient. D is the average diffusion coefficient into time divided by r square. R is the radius of the circle in the region where he is walking. And for a free diffusion, that means no crowding, you see you have this dotted line as the result. If you plotted logarithm of the survival probability as a function of time, which essentially means that you see in this it is exponentially decaying. But then in presence of crowding, the rho is a measure of the crowding. In presence of crowding, as you increase the crowding, what happens is that the survival probability increases and it definitely becomes non-exponential. So essentially the survival probability is a multi-exponential. Now we have to think of a different problem. I mean, these are the results that we could obtain analytically, and we published those results in the Journal of Physical Chemistry. I would like to know about time. How much more time do I have? Could somebody answer that? Sajesh or somebody who must be listening?
Sir, yes, sir, yes, sir. Like 15 minutes or more. I mean, as you wish, sir. There's no.
Okay, yeah, well,
roughly around 15 minutes.
I should be able to finish in 10 minutes and then maybe 5 minutes of questions if you like.
Yeah, that should be
Or
perfect.
even lesser, even lesser, okay. So rotational diffusion, rotational diffusion is simple. Imagine you have a rather big molecule which has a transition dipole, let us say. This shows the direction of the transition dipole, and imagine it is undergoing rotational motion. As a result of which, you see the molecule's orientation changes. So therefore, of course, this is happening in a condensed medium, so homogeneous condensed medium, and then the orientation will change in a random fashion, and this orientational change is what is referred to as rotational diffusion. So how will you describe rotational diffusion? Well, if it was happening in 2 dimensions, you see, you get such an equation. I will not go into the details of this, but the thing that you should notice is that the diffusion coefficient is sitting here. And because this is happening in 2 dimensions, you see the orientation is specified by just one angle phi. And if you are careful, I'm sure the students will notice that this is actually very similar to the time-dependent Schrodinger equation for a rigid rotor, but it is rotating in 2 dimensions only. So this is the Hamiltonian operator, if you like, for a rigid rotor. And on the left-hand side, you have time derivative of the wave function in the case of quantum mechanics, but here it is the time derivative of the probability distribution. So essentially, the problems are very similar. And you know that the Schrodinger equation for a rigid rotator in 2 dimensions or in 3 dimensions can be exactly analytically solved. So therefore, this is a very easy problem to solve. Let me not go into further mathematics of this. And if you plotted the probability distribution by solving this equation, this is the kind of behavior that you will get. And if you look at this behavior, you see it is at short times, it is exponential. Even at longer times, it is exponential. But eventually, at long times, you see the rotation can take place only over a finite angle. So therefore, it becomes uniformly distributed. That is the analytical result if you are thinking of a crowded medium. Well, this is in 3 dimensions, homogeneous rotational diffusion in homogeneous medium in 3 dimensions. It is described by a similar equation. Like the previous one, this is a rigid rotator in 3 dimensions, essentially equivalent to a rigid rotator in 3 dimensions. But then what happens in crowded media? Well, so how did they do the simulation? Well, these simulations were done in 2 dimensions. You have disks, right? In the hard disk, maybe I should simply write it down if it is not clear what I am speaking. So these are all hard disks which were randomly placed, and then they introduced a dumbbell. Why a dumbbell? Well, the dumbbell can rotate. These were actually held stationary. But the dumbbell was free to move and it was free to rotate. And they placed several dumbbells and then looked at the rotational motion of these dumbbells. And if they study the rotational motion of an individual dumbbell, well, you will find that there is a quantity phi that is sitting here. Phi is actually the density of crowding. This is the volume fraction occupied by the crowders. So these simulation results were obtained at phi equals 0.3. So if you look at the probability distribution of angles for an individual dumbbell, then what you find is that it is Gaussian, right? It is Gaussian, but then you look at all of them collectively, then you find that it is exponential. So that is the experimental simulation result. So then we thought of constructing an analytical result. Well, I should also tell you that, you see, people have tried to do experiments with such systems in crowded medium. In fact, Arindam Chowdhury at IIT Mumbai has done the experiments, but unfortunately they were not able to measure the probability distribution. They were able to measure only the angular distribution. So therefore, this cannot be really compared with our analytical results, because as far as I know, there is no experimental result available which measures the probability distribution of the angle as a function of the angle. Okay, this is actually the mathematics of it, let me not go into it. But essentially, our simple analytical model could be solved exactly analytically for this case also. And these are our analytical results. At short times, what do we find? We find that the probability distribution as a function of the angle phi is exponential, just as in the previous case, where we were concerned with translational diffusion. But as time passes, that probability distribution changes over. It is looking more and more like a Gaussian. But of course, in the t tending to infinite time limit, it becomes a flat distribution. So this is our theoretical prediction. As I said, there are no experimental results done with real molecules yet, but hopefully Arindam will do the experiment, will be able to do the experiment and get the experimental results and compare. So these are at different times, as you can see. But then you see, when this 2 or 3 slides, which I will very quickly go through, telling you just the results. When we were in the process of submitting these papers, the referees asked questions. You see, they said, see, there are experiments in biology where the diffusion coefficient has been observed and its probability distribution has been determined experimentally. Diffusion constant, as I told you, is itself random, and people have experimentally determined its distribution, and they found that many times these probability distributions have long tails. And when the referee raised such a question, my student Rohit Jain, who did this analytical calculation, said there is not a problem. But before I tell you about his approach, I just want to show you a probability distribution which has a long tail. If you look at this, you see this particular distribution has a long tail, and so is this one, or even this one has a long tail. So what do you mean by long tail? Well, in the tail portion, the probability goes like d to the power of minus alpha. That is the meaning of saying that it has a long tail. So my student was able to construct a model. As I said, we will not go into the details of this. But if you look at this, you see this is actually the equations that we had to solve. This accounts for the fact that it has a long tail, and this portion accounts for the harmonic potential, which we have to have in our model. And this actually accounts for the absorption. So we could solve this analytically, and what is the result? The result is that the width of the distribution measured by sigma, or actually here I am telling you about sigma square. The square of the width is proportional to time at short times, and it is proportional to t to the power of 1 by alpha at long times. Alpha is a parameter which determines how long the tail is, and this was published. The referees also asked what happens if D undergoes sub-diffusion. This is a little bit technical again, but finally what we found was that the results are similar to the case of normal diffusion. So I don't have to explain to you anything. This is the model. But anyway, let me now go to the conclusions. We have a simple analytical model for diffusing diffusivity. In fact, this was the first model ever, in which we showed that it can be reduced to a problem of random walk with absorption. And we were able to get exact solutions for a variety of problems. For example, survival probability in a bounded region, diffusion, which is of importance in diffusion controlled reactions, long tail diffusivities. Well, these were some of the other papers that we published, and let me now end up with the acknowledgement. You see, I am infinitely grateful to the Indian Institute of Science, which essentially made me what I am. Was a student there, then later on I became a faculty member. And in fact, my thinking in theory was essentially determined by my mentor, Professor S.K. Rangarajan, who was not my PhD supervisor, but I interacted with him while I was at the Institute of Science as a student, and the Department of Inorganic and Physical Chemistry, from which I did my PhD, and then eventually I became a faculty member there, and I have had infinite support from them. And the DST Government of India, which has given me a J.C. Bose Fellowship, and other things. So I would like to thank you. I hope I have not bored you with all these all these equations, but the pictures that I have shown hopefully would have kept you attentive. I hope. Thank you. Thank you all for your attention. Thank you. I would, of course, like to thank the Department of Chemistry once again for this wonderful opportunity to be talking to the students and faculty of the department.
Thank you. Thank you, Professor Sebastian, for the insightful and stimulating talk and teaching us so much about diffusion. And it was really also nice to finally see Captain Haddock understand some equations. Yeah.
Okay,
And,
okay. I'm happy to hear that.
yeah, and I would now like to request Professor Thomas to conduct the Q&A session. Over to you, Professor Sajesh.
Thank you, Dr. Swamik. So, if any of you have any questions to Professor Sebastian, please type down in the chat box. And I'll start with the first question, which is asked by Karuna Vihan. She's typed down. So, sir, you told that we cannot allow diffusion coefficient to go below 0. So, is it possible to have negative diffusion coefficient under any circumstance? If yes, could you please shed some light on that?
Yeah, well, you see, you have to look at the fundamental definition of diffusion coefficient. It is x square average divided by time. So even in the definition of the quantity, you see, you have x square, x is the displacement. So displacement square divided by t is the diffusion coefficient. So therefore, it is impossible for it to be negative. I hope that answers your question.
Thank you, sir.
See,
I hope
it is the way you define the diffusion coefficient. Diffusion coefficient by definition is a square divided by the time. So when you do an experiment, you see, and of course, having a diffusion coefficient negative would be completely unphysical. Because what I expect is that, you see, particles will move from lower concentration to higher concentration. You see, normal diffusion would happen from higher concentration to lower concentration. But if you had a diffusion coefficient which is negative, the particle, instead of moving in the direction where the concentration is decreasing, the particle would on an average diffuse in the opposite direction, which will not happen physically. I'm using essentially the Fick's law to make this argument. I hope that is clear.
Sebastian.
Hello, Ram. I was wondering that I've not spoken to you.
No, I'm not in Delhi, but I really enjoyed the talk, Sebastian. I was wondering, with the are there some nice newer experiments that your theory is suggesting? Because the agreement of your analytic curves with the data is fantastic.
Yeah, it's very good, surprisingly good, actually.
Well, no. So, is there an experiment that you can suggest? Something that I mean, I love the worms example, but we can't do things to worms. There may be Maneka Gandhi will get after us for that. No, it's okay. So more seriously, what would be good what would be good situations to test some of the other predictions that your theory has?
Yeah, well, you see, obviously the rotational diffusion in crowded medium, we don't have any experience done with molecules. As I said in my talk, it was Aridham Chaudhary who pointed this out to me. In fact, I went to IIT Mumbai and then only I realized it. He has been actually trying to determine the angular distribution in crowded medium. But his experimental resolution, he says that is not good enough. So if he reaches that experimental resolution, measuring the angular distribution, then we would definitely be able to compare, but we don't have. I mean, as of now, nobody has reported an experiment that I know of.
Okay.
So that would be a fantastic experimental observation that will confirm this.
Yeah, no, Arindam gave a talk in the department a couple of years ago, but I must confess the details have.
Yeah, well, he has not published anything. In fact, I gave a talk very recently at the CRSA meeting. Arindam was there, and after the talk, he did not tell me that he now has results.
Okay.
He was in the audience.
Right. Okay, nice. Thanks.
Ram, it is nice to talk to you after such a long time.
I know it's been ages, huh?
Yes.
Yeah, well, hopefully in person soon.
Well, you see, I'm in Bangalore, but I'll go back to Cochin. I am not healthy these days, so it's very unlikely that I will travel.
Okay. No, I was going to come to Bangalore in December.
December, I may be here, definitely.
Okay, and then I'll come by and see you. Yeah.
Let me know when you are in Bangalore.
For sure. Yeah.
Okay.
So can you switch on your video? Mr. Sebastian, can you switch on your video?
Switch on.
Yeah.
You cannot see me. Okay. I have to quit this.
I mean, we could see before, but now.
Yeah. One second. Let me quit this presentation. I will quit the Q0 presentation. Then where am I? I am sharing my screen. Maybe if I stopped it, stop sharing.
Yeah, if
okay,
you
let
hover.
me stop sharing.
Yeah, now it's fine.
Okay, fine. I should be visible now.
Yes.
Yeah.
Okay.
So thank you. So I don't see any more questions in the chat box. So
yeah, well, I'm always worried whether because you see it's equations. I hate talking about equations, but that's my bread and butter.
Okay.
over to you, Shamik. Yeah.
Okay, so if there are no more questions, so I'd like to thank Professor Sebastian again for joining us today. And when all this COVID crisis gets over, probably someday we would like to host you physically here at IIT Delhi in our department.
That would have been very nice, actually. I have come there, of course, but sitting once again would be nice.
Yeah, like hopefully it will happen someday. And I also like to thank Professor Kurur, our HOD, and Professor Ramaswamy for their constant encouragement, and also Professor Janakiram, Divyajyoti, and Vishwarup for co-organizing this webinar series with me, and also Professor Sajesh for coordinating this particular lecture. And On behalf of our department, we would like to wish you good health in these difficult times, and take necessary precautions, and please stay safe, and have a great evening. And thank you.
Thank you very much.
Thank you, sir. Thank you, sir.
Thank you, sir.
Yeah, shall I sign off now?
Yes, sure.
Professor Kuru,
Okay,
so Kuru is here. And,
Professor
yeah,
Kurur.
hello, Kuru, Professor Kuru.